The last video in this large solutions chapter talks all about the colligative properties of our solutions. Okay, this term colligative is different and you haven't seen that yet before. But what colligative refers to is that there will be properties that depend on the concentration of your solute in the particles, but not necessarily their identity. So it's more of a how much is in there versus what is in the solution. Okay, so the big example that we talk about is how the vapor pressure graph is changed when you start dissolving things in water. So how do the normal typical properties of water get affected? Um, and the biggest example of this is there is something called freezing point depression, where we change the freezing point and we can actually lower the temperature at which um, water is going to freeze, and boiling point elevation, which is the opposite. We're going to see how when you dissolve something in water, how it changes that boiling point from 100 to something else. So real life freezing point depression and boiling point elevation. Okay, everybody knows what these things are. Well, at least everybody here in our part. This is a salt truck. Okay, the salt truck is not going to put NaCl. Okay, it is going to probably put CaCl2, something that has a dissociation factor that is pretty big. This has a dissociation factor of 3. And it is going to change the freezing point of water, which is 0 degrees Celsius, and it is going to drop it. Okay, but there comes to a point where it doesn't have an effect anymore. So you'll see that places that are really cold, like upper Minnesota, our family up in Maine, they don't really use a ton of salt because it gets below those temperatures. Okay, so this can lower all the way down to about negative 20 degrees Celsius. And then after that point, you're kind of out of luck. So then they use sand for traction, but they don't get as much ice as we do here in Abington, Pennsylvania. Okay, you'll see this stuff, those of you that are starting to learn how to drive, this is called antifreeze. Okay, it's antifreeze and anti-boil. So it is actually going to do two things. It's going to cool down your engine without freezing it and without it boiling. That is this green gunk right here. Okay, this is ethylene glycol, ethylene glycol, which they actually synthesize now after isolating it in fish that lived in the Antarctic. And they were like, why are these fish not freezing? So that's how they came about. Because if you don't use antifreeze and you use water in your engines, it will boil or it will freeze in cold temperatures, and then it won't be able to cool, and then you see these cars overheat and all that bad stuff. And then we obviously know that we salt pasta water when we are cooking. It's going to raise the boiling point ever so slightly, but it does raise the boiling point, so it actually cooks with less time when you salt your water. Uh-huh. You didn't know that, but that is a fact. Drop some knowledge on you right there. All right, so what do we see with freezing point depression? Okay, this right here is our phase diagram that we went over in states of matter. Okay, phase diagram. And this is for H2O, okay, for water. Okay, in a phase diagram, we have our typical vapor pressure of our solution, which is going to be this blue curve right here. This is the solid portion, this is the liquid, and this is the gaseous portion. Okay, this is the specific temperature and pressure that you will be in for all those different things. Okay, so the vapor pressure of the pure solvent is, I'm sorry, I said that wrong. The pure solvent, so pure H2O, is this pink version here. Okay, and the solution, once some salt or any general other salt is added, is actually going to widen this curve. Okay, so it goes from here out to here, and it goes from here out to here, and it actually extends where water is a liquid. Okay, so less gaseous region, less solid region. Okay, and this is data that they found out. So if you are looking here at our 1 atmosphere of pressure, this is 0 degrees Celsius, it's actually going to lower the temperature and it's going to freeze at some -degrees Celsius. Okay, so this is given the symbol delta TF. So delta T, change in temperature, F as in freezing. That is what we use for freezing point depression. So the difference between the normal temperature in which the freezing points of a solution and the pure substances are is going to be our delta TF. It is directly proportional to the molal concentration of the solution. Okay, so molality is that lowercase m, moles of solute per kilograms of solvent. Okay, so when we know that, we are going to use this delta TF equation to figure it out. Okay, there is a molal freezing point constant. This constant where we end up having for water, okay, um, a specific amount that the temperature will drop in freezing point for every molal of the solute. So this would be given to you, the KF for water, and it's different for different substances, obviously, is -1.86. So if we have 1 mole of solute, it's going to drop -1.86 degrees. If we have 2 moles, oh yeah, it's going to do double that. So it's going to be -3.6 degrees, etc., etc. Okay, but you also have to factor in, oh, look at that, dissociation factors. Okay, that also is applicable in this scenario. Okay, so it depends on how many ions it breaks up to. If you're talking about adding sugar or alcohol to water, since those are covalent solutes, since they don't break up into ions, their dissociation factor is 1, and it isn't going to depend in that scenario. Okay, boiling point elevation does something similar but opposite. Okay, so our pure solvent is going to be right here in the pink. Okay, and as we know, this is where our substances are solids, liquids, and gases. When you add a solute to water, it's going to extend the range of the liquid phase. So if this is our 1 atmosphere of pressure, okay, we are going to see that we are going to extend from 100 degrees Celsius, which is right here, over here, and it's going to increase, so it's going to be 100 point something, or 101, or 102, yada, yada, yada. And that is given the symbol delta TB, the change in temperature, boiling. Okay, so the difference in temperature between the boiling points of your solution and the pure solvent is likewise directly proportional to the molal concentration of the solution. It's given that symbol delta TB. Okay, and it has, again, a very similar equation. Delta TB is the KB, which is the boiling point elevation constant for water. Okay, it is 0.52 degrees Celsius per molal. And again, we see our dissociation factor being a factor in there. And remember, our covalent solutes have a dissociation factor of 1. Okay, so the delta TB is always going to be this constant, and the KB is not equal to the KF. All right, so don't confuse the two, and they would be something that would be given to you and nothing that you would have to memorize per se. All right, so let's apply it. Let's do a sample problem. What is the freezing point depression? Okay, so we're looking for freezing of water in a solution of 17.1 grams of sucrose, which is C12H22O11, in 200 grams of water. And what is the actual freezing point of the solution? So we don't want to know just the delta TF. We want to apply it to the 0 degrees Celsius that we know is the freezing point of water. Okay, so let's solve it. You got a problem, I'll solve it. All right, so KF, sorry, let's go back. Okay, delta TF is equal to the KF times the mole concentration times the dissociation factor. Okay, so the KF is going to be our negative 1.86 degrees Celsius per mole, because we want to know how much it's going to lower. So now we need to figure out the molality. So side calc, molality is moles of solute per kilograms of solvent. So if I have 17.1 grams of C12H22O11, you need to change that to moles. Okay, so 1 mole, and then we look on the periodic table and we get 12 carbons, 22 hydrogens, 11 oxygens, and that is 342.34 grams, and that gives you 0.05 moles. Okay, how many kilograms of solvent do we have? Well, we have 200 grams of water, which is our solvent. We need to change that into kilograms. So there's 1,000 grams in a kilogram. So this is 0.200 kilograms of water. So get your calculators, go run, go get them. Okay, and figure out your molality. Okay, molality is 0.05 divided by 0.2, and this is going to give us a molality of 0.250 molal. So this gets plugged in over here, 0.250 molal. Dissociation factor, it is sugar. Oh, how sweet. Is this ionic or covalent? No ions in here, so the dissociation factor is 1. Safe. Woo! So now, delta TF is equal to negative 1.86. Plug it into your calculators. 0.250 molal, which is going to give me a delta TF of negative, and it should definitely be negative, 0.0465 degrees Celsius. Molal and molal is going to cancel out. All right, so what do we do? Okay, what is the new freezing point? 0 degrees Celsius plus negative 0.0465 degrees Celsius, you guessed it, is negative 0.0465 degrees Celsius. That is our final answer. Be careful if you are doing boiling point elevations, okay? If you are talking about delta TBs, you have to add to the 100 degrees Celsius in order to get a new boiling point. So it's not going to be, boiling at 2 degrees. It's going to be boiling at, say, 102 degrees. So be definitely mindful of that one. All right, so here are our explanation of the whole thing. Typed out for you if you can't read my stuff. We change our grams of sucrose into moles of sucrose and then divide moles by kilograms to get my molal concentration. This goes into our delta TF equation. The KF is our constant, a dissociation factor of 1 because it is covalent. And then we add to 0 degrees Celsius to get our new freezing point of water, water, water. And that, my friends, is how we do colligative properties. Hope you enjoyed. Ta-ta for now.